Hi everyone, this is the Lesson 3 Extra Practice Guided Study Group session for ECON315. So today's problems have a lot of math in them. This session will be one of the longer ones, but I'm going to get started right away. So question 1 has to do with marginal outputs of labor and capital. So it says a new type of technology is developed that allows standard motor product to produce fuel injectors using capital rather than workers. The daily production choices faced by the firm are in the table below. Solve for the missing values. So I'll get to that in a second, but just to give you an idea, we're going to have to fill in this table and then analyze it. So switching my screen, you can see that I already created the table. Hopefully it's not too hard to read. Like I said last week, this tablet isn't the best in making things legible, but I try my best, so bear with me. The table is included in the problem online in Canvas, so you can reference that if that's a little easier and fill it in on your own. So the first thing they wanted us to do was fill in this table. So the first column is marginal product of labor, which is going to be the additional output produced with each additional worker. In this table, we see that each worker is going up by 1, so we can easily just take the difference between each of these. So the marginal product of labor for worker 0 is going to be nothing because it's not increasing from anywhere, like that's the starting point. So then we see for the first worker, the marginal product of labor is 100 because we can get that from taking this difference. Like I said, the marginal product of labor is the change in additional output over each change in worker. So we're looking at the change per one worker, not per like 5 or 10. But anyway, looking at the second worker, the marginal product would be 50. The next one would be 40. The next one would be 35. And lastly, we would have 25. And then we do the same exact thing over here with the marginal product of capital. They give us each unit of capital that could be used, the output with each of those allotted units, and we can just take the difference from each one since these units are all going up by 1. So this first one's going to be nothing, and then we have 50, 45, 40, 35, and 30. So that was part 1, solve for the missing values. Next part, it says if each fuel injector is sold for $5, so the price equals $5. If each fuel injector is sold for $5, plot the marginal revenue product of labor against the number of workers. Label your axes. So they ask us for the marginal revenue product of labor, which we haven't solved for. So my recommendation is to create another column and expand this table. So I'm going to use this first column I created and label it marginal revenue product of labor. And we know that the marginal revenue product of labor is calculated by taking the marginal product of labor, which is each worker's additional output, multiplied by the price of the item or the output being sold. So in this case, our price is $5, which is also looked at as our marginal revenue. So what we can do is multiply each of these marginal products of labor by 5. So the first one is still just going to be nothing. The second one, we're going to take 5 times 100 to get 500. Next one is 5 times 50, which is 250. 5 times 40, which is 200. 5 times 35, which is 175. And finally, 5 times 25, which is 125. So now that we have the marginal revenue product of labor, it wants us to plot that against the number of workers and label our axes. So we can just create a simple XY graph. In this case, the x-axis is going to be our amount of labor, and the y-axis is going to be our marginal revenue product. So we can label that marginal revenue product of labor, and then the amount of labor. And then we can just line up these values on each axis and then connect the points. So we can label the origin, and then we have 0 to 5 workers. So 1, 2, 3, 4, 5. And then for our marginal revenue product axis, I'm going to start at 500 at the top. And try to make everything as symmetric as possible. So sorry, my mind blanked on what I was labeling there. So I'll keep going though. So what I'm going to do is just label the hundreds. So 100, 200, 300, and 400. And then we can also see that in between is going to be in 50s. But you can probably draw a nicer graph on your paper when doing these problems. So I'm just trying to do this best I can on here. So anyway, now you have to plot it. So for 1 unit of labor, we see that the marginal revenue product is 500. We put a dot there. For 2 workers, it's 250. 3 workers, it's 200. 4 workers, it's 175. And then 5 workers, it's 125. So we can see there is some kind of trend, and we can just draw in a curve to connect this the best we can. So that is everything for number 1. We labeled the axes. We figured out the marginal revenue product, labeled the axes, and then plotted this relationship. So then for number 2, it says if the daily wage is $100 per worker and the cost of a unit of capital per day is $60, how many workers and how many units of capital should the firm utilize in order to minimize the cost of producing 350 fuel injectors? So for number 2, they tell us the cost, the daily wage per worker is $100, so W equals 100. And then the cost of capital, which I'm just going to denote as R, is $60. And they want us to figure out how many units of capital should the firm utilize in order to minimize the cost of producing 350 fuel injectors. So minimizing the cost, we're going to be trying to find some combination that gives us profit maximization. So profit maximization, which I'm just going to label as profit max, is going to be when the marginal product of labor per wage equals the marginal product of capital per the cost of capital. So what we're looking for is that for each dollar paid to a worker, their output is the same as the output given from capital for each dollar of the cost of capital. That's when we're going to maximize profits. So in this case, we have to find each of these. We have to find where these two values meet each other, and we have all the information for that, but we haven't done the calculations yet. So that's where this last column, these last two columns come in. So this first one I'm going to put as marginal product of labor over wage. And then I'm going to put this one as marginal product of capital over R. So we know that the marginal product of labor for this first row is both going to be nothing. For this second row, I'm going to do the first column all the way down. So we're going to have marginal product of labor, which is 100, over the wage, which they gave us was 100. So we can see that this equals 1. The next one, we're going to have 50 over 100, which equals 0.5. 40 over 100, which is 0.4. 35 over 100, which is 0.35. And then finally 25 over 100, which is 0.25. Now you can do the same exact thing with the second column. So we have 50 over 60 because the cost of capital is different than the wage. So we now have 50 over 60, which gives us 0.83. 45 over 60, which gives us 0.75. 40 over 60 is 0.67. 35 over 60 is 0.58. And finally, 30 over 60 is 0.5. So looking back at what I told you was profit maximizing, we need to find a value that satisfies this equation. So in this case, what we need to do is find a value that's the same in both of these columns. And we can easily see that this is going to be 0.5. So what this tells us is, looking back at a marginal product of labor per wage of 0.05 is associated with 2 workers. And a marginal product of capital per cost of capital of 0.5 is associated with 5 units of capital. So this tells us that by using a combination of 2 workers and 5 units of capital, this is going to minimize the costs and profit maximize for producing these fuel injectors. So a way to check it is they gave us the number of fuel injectors they wanted to produce, which was 350. So output was 350. To check this, we can just make sure the amount of output produced per production choice, I guess, adds up to 350. So for 2 workers, looking back at our table, 2 workers produce an output of 150. And then 5 units of capital produce an output of 200 fuel injectors. So we can see that this equals 350 and these two match up, which satisfies our answer. So that is all of the first one. It was a really long question, but the biggest thing was filling the table and then knowing how to analyze it, and then my recommendation of creating new columns to figure out the rest of the information needed to answer the questions. So moving on to the second one, marginal product, marginal revenue product, and marginal profit. So the output of bakers at the local bakery depends on the number of bakers employed. Factory sells its cheesecake in a competitive product market at a price of P equals $10. Daily wage of bakers is W equals 600. Fill in the marginal product of labor and marginal revenue product of labor columns in the table below. So this one is just like, well, the first part at least is just like the last question we did where we need to fill in these things. So okay, so I drew the table as best I could. It's decent enough to work. So this is going to be bakers, total output, marginal product of labor, and then marginal revenue product. And then we have 0 through 8 workers. And then they also give us the total output, so 0, 500, 860, 1160, 1400, 1560, 1640, and then the last two are both 1680. So the first part was fill in the 2 columns. So we just did this the last time. So the marginal product of labor for 0 bakers is just going to be 0. And then since each of these bakers go up by 1, we can just take the difference of total output, because technically our equation is the change in output over the change in labor. That's technically what our MPL equation is. But in this case, because each of these bakers are increasing by 1, we can just take the difference of total output. So we have 500, 360, 300, 240, 160, 80, 40, and 0. And then they told us at the beginning that the price of cheesecake is $10, and the daily wage is $600. So to find marginal revenue product, we're only concerned with the price, so we can take that multiplied by the marginal product of labor. Price times labor. So we can do 500 times 10, which is 5,000. The next one would be 3,600, 3,000, 2,400, 1,600, 800, 400, and 0. So that is all we need to do for that first part. Then it asks some questions, and it says, how many bakers should the manager employ? So we have to always look at the margin in making these decisions, always looking at the marginal product of labor and marginal revenue product, the wage. But the concept is always thinking on the margin. So usually in profit maximization, we're going to want to produce where marginal revenue product equals the wage. But in this case, the wage is $600, and none of these are also $600. So because of this, we're going to want to produce up to the point where the marginal revenue product is greater than the wage. And this makes sense because our profits, like we want to be making money, not losing money. So if we're paying workers more than what we're bringing in as revenue, we're going to be losing money. So we don't want to have it the other way around of wage being greater than marginal revenue product. We always want it the opposite way of marginal revenue product being greater than the wage. So we can see that this occurs, that producing up to this point occurs at worker number 6. So we know that the manager should employ 6 bakers because of this idea of profit maximization and looking at the margin. So question number 2 says, what is the marginal profit of the last worker hired? So this profit is just going to be the difference between the marginal revenue product and the wage, which we can see just by taking marginal revenue product minus the wage. For this sixth worker, that's going to be 800 minus 600. So we get a marginal profit of $200. And then how much total profit does the bakery earn? Total profit is going to be the total revenue minus the total cost. So total revenue in this case, we can calculate by taking the price of the cheesecakes times the total output produced. And then total cost is going to be the wage times the number of bakers. So we can see this is going to be 10 times 1640, which is going to be 16,400. And then the number of bakers times the wages is going to be 6 bakers times a wage of 600, which is 3,600. So we can see that taking this difference, that the result is a profit of $12,800. And that is everything for number 2. So pretty similar to the last one, filling in a table and then analyzing it. A little bit different kinds of calculations, but not too bad. So then moving on to number 3, it's about payroll taxes and demand. The government levies a payroll tax on firms, requiring firms to pay $2 per labor hour. Prior to the tax, aggregate labor supply is labor supply equals 40 plus 15W, and labor demand is given by labor demand equals 200 minus 5W. So this question has to deal with equilibrium, which we worked a lot on last week. So they want us to find the equilibrium before and after this tax. The payroll tax makes us change our equation a little bit, but it's a fairly simple concept. So I'm going to write out the equations they gave us. Labor supply equals 40 plus 15W. And then labor demand is 200 minus 5W. So before this tax, nothing is affected. So we can just set these two equal to each other and solve as we did last week. So we have 40 plus 15W equals 200 minus 5W. So we can subtract 40 from both sides to get 160 on the right, and then add 5W to both sides to get 20W on the left. Then dividing both sides by 20, we get an isolated variable of W of $8. So the equilibrium wage before the tax is going to be $8. We can plug this into either equation since we're at equilibrium. So labor supply equals labor demand. So I'm going to use the first equation. So equilibrium level of labor equals 40 plus 15 times 8, which becomes 40 plus 120. So we get an equilibrium labor of 160. So in equilibrium, we have 160 workers getting paid $8. Now we have to apply the tax and solve for equilibrium. So thinking about how to put this tax into the equation, they said the payroll tax was $2. So requiring firms to pay $2 per labor hour. Well, if you look at our equation, or what we know about these equations, our wage is paid by the hour. So for these firms, paying $2 per labor hour is going to make it more expensive to pay by the hour. So if we were to put it in terms of wage, our wages would go up by $2. So when we rewrite this equation, we can turn this W variable into W plus 2. So we still have the same supply side, but we're going to change this demand side to have it 200 minus 5 times the entire quantity of W plus 2. Like I said, we're adding 2 because it's more expensive to hire labor per hour. And then we can just use some algebra to solve it like normal. So keeping this side the same, 40 plus 15W, we have 200 minus 5W, then distributing the negative sign minus 10W. Combining like terms, 200 minus 10 is 190. If we subtract 40 from both sides, we know that 190 minus 40 is 150. And then adding 5W to both sides, we can get 20W on the left. Dividing each side by 20, we get a wage of $7.50. And then, like I said, we can plug this, like last time, we can plug this into either equation since we're in equilibrium. So I'm going to use the first equation again, 40 plus 15 times a wage of $7.50. This gives us a equilibrium labor level of 152.5. In this course, it's okay to have fractions of workers. That's just how the math works out. Don't freak out that you have only partially of a person in these answers. But that is all of part 1. So then it says, what fraction of the payroll taxes paid by firms is passed on to workers? So we know the payroll tax is $2. We can look at the equilibrium wage to solve this. So we can see that after the payroll tax, the wage goes down by 50 cents. So they're losing 50 cents from this tax. The overall tax is $2. So if we create this fraction, we can see that 25% of the tax is passed on to workers. Because if you think about it, the firm paying $2 per labor hour, it's going to be more expensive for them. They're going to have to increase their costs somewhere, meaning if they want to try to even it out, they're going to have to decrease their costs somewhere else, which in this case is in the wages for workers, which this 50-cent decrease makes up 25% of the overall payroll tax. So hopefully that all makes sense. The next problem is pretty similar, but I'll move on to that. Question 4, payroll taxes and demand with inelastic curves. So referring to the previous question, suppose labor supply curve is instead perfectly inelastic and given by labor supply equals 160. Re-answer questions A and B from the previous question. So I should be able to fit it on here. So this is for the new one, number 4, in this corner. So the labor demand equation hasn't changed, but the labor supply equation has. So before we have 160 equals 200 minus 5W. So we can solve for W by adding 5W to both sides and then subtracting 160 to both sides. And we get an equilibrium wage of $8. So just a little bit of explanation for what they were saying. They wanted the labor supply curve to now be perfectly inelastic. So if you were to look at this on a graph, it'd be vertical. So by making the labor supply curve perfectly inelastic, where people aren't as sensitive to wage changes, we want to see how this impacts the payroll tax. So we have a wage of, so back to the problem, we have an equilibrium wage of $8, and we can plug that back in either way, but we really don't need to plug it in because we know that this side has no variables. So we can also just see that equilibrium labor is 160. If you'd feel more comfortable just plugging it back into the labor demand equation, you could do that, but you'd still get the same answer. And then for after, we do the same exact thing with the wage and the $2 payroll tax. So we have 160 equals 200 plus, nope, 200 minus 5 times the quantity, excuse me, of W plus 2. And then solving this out, we get 160 equals 200 minus 5W minus 10. Solving for this, we get 5W equals 30. So the wage is now $6. And then we still know that the labor is equal to 160. And then they want us to find the same exact fraction of the payroll tax paid by firms. So we can do this the same way we did last time. So the difference of the equilibrium wage before and after is $2. And we also know the payroll tax is $2. So we can see with a perfectly inelastic labor supply curve, 100% of this tax is passed on to workers. I guess thinking more about it, if workers are perfectly inelastic to wages, meaning they'll still supply it no matter what the wage is, firms are okay just having the entire expense laid on them because they're not going to respond and change whether they stay in the labor force or not. So 100% of that tax is put on workers. But anyway, that is all for question 4. So moving on to the next one. There's a lot of questions in this chapter, but we can keep going. So, to decrease the number of individuals on welfare, the U.S. government agrees to subsidize the employment of either current welfare recipients or individuals who have been on welfare during the past year. Specifically, the government will pay firms $4 an hour for each worker employed meeting these requirements. Prior to the subsidy policy, the labor supply of welfare recipients is given by labor supply equals 20 plus 5W, and labor demand is given by labor demand equals 120 minus 15W. Calculate the level of employment and the equilibrium wage rate before and after the subsidy goes into effect. So, essentially the same kind of questions or situation as last time, but instead of a payroll tax, it's now a payroll subsidy. So this is going to affect our equation a little bit differently than the last time. So we just know beforehand that this subsidy is going to be $4 an hour. And they give us our equations of labor supply and labor demand, which is 20 plus 5W. And then labor demand is 120 minus 15W. So beforehand, the tax or the subsidy doesn't apply. So we can just solve these two as we've been doing all of last week. So we can just set them equal to each other. So 20 plus 5W equals 120 minus 15W. So adding 15W to both sides, we get 20W, and then subtracting 20 from both sides, we get 100. Dividing each side by 20, we get a wage of $5. Plugging that back into either equation, I'm going to use the first one. We have equilibrium labor equal to 20 plus 5 times equilibrium wage of 5. So 20 plus 25 gives us 45. So that is the equilibrium wage and labor for before this payroll subsidy. And then they ask us to calculate after. So thinking about after, you can set it up the same way so far. Labor supply is going to be 20 plus 5W. And then we have to look at the demand equation and change that. I forgot to mention last time, we are putting this change on the demand equation and only the demand equation because this payroll tax, or in this case subsidy, is impacting firms. The labor demand curve represents firms. So that's why we're putting in these changes on the demand side and not the supply side. I did not make that clear last time, but hopefully that makes more sense now. You can't just pick either one at random. You have, when talking about payroll subsidies or taxes, you have to use labor demand since these things are impacting the firm side. But anyway, we have our labor supply equation and then labor demand, which starts off as it usually does, 120 minus 15. But now we have to multiply that by the whole quantity of W minus 4. So think this subsidy is making it cheaper for firms to hire labor and pay them per hour. So it's going to lower their costs. So it's going to be $4 lower than what their wages. The firm is going to have to pay $4 lower than what they would usually pay for wages from this subsidy. So that's why we have the minus 4 at the end there. Then we can solve this just using algebra. So 20 plus 5W equals 120 minus 15W. And then distributing the negative, we have plus 60. Combining like terms, we have 120 plus 60, which is 180 on the right. Subtracting 20 from both sides, we then get 160 on the right. And then adding 15W to both sides, we get 20W on the left. Dividing each side by 20W, we get a new equilibrium wage of $8. And then plugging that back into either equation as we've done, we can see that the equilibrium labor is 20 plus 5 times 8, which is 20 plus 40. So we get a new equilibrium labor of 60. So that is all for number 5. Number 4 and number 5 are very similar. It's just whether it's a payroll tax or a payroll subsidy. Like I said earlier, these taxes and subsidies are going to affect the firm. So with them affecting the firm, this is going to impact our labor demand equation, not our labor supply equation. But that's all for this one. So I think we're on the last question, which is about minimum wage. So in an economy, labor demand equals 125 minus 5W, while labor supply is 20 plus 10W, where W is the hourly wage rate. Once again, what is the equilibrium level of employment and wage? So from last week and then what we've done this week, everybody should hopefully be pros at this now, but I'm still going to write everything out. Labor demand equals 125 minus 5W. And labor supply equals 20 plus 10W. Equilibrium, we can just set them equal to each other. So 125 minus 5W equals 20 plus 10W. Adding 5W to both sides, we get 15W on the right. Subtracting 20 from both sides, we get 105 on the left. And then dividing each side by 15W, we get an equilibrium wage of $7. You can plug that back into either one. I'm going to use labor supply. So equilibrium labor is going to be 20 plus 10 times 7. So 20 plus 70 is 90. That is our very quick solution to solving, very quick solution to equilibrium for this problem. So the next one, it says, if the present minimum wage is $5.85 an hour, and the government raises it to $6.50 an hour, how many workers will lose their jobs, and what is the unemployment rate? So thinking about a minimum wage is a price floor, meaning that whenever that price floor is set, firms cannot set a minimum wage and anything below that. That's what's meant by a price floor. They're prohibited from doing so. So the thing with price floors, though, is they're only effective if they're above equilibrium. If price floors are below equilibrium, it's non-binding because if a higher wage is going to put the market in equilibrium, that's what firms are going to choose. So a minimum wage below the equilibrium wage isn't effective. It's non-binding. Firms are still going to choose to set their wages higher to put the market in equilibrium, which I just said. But anyway, looking at this minimum wage change from $5.85 to $6.50, it's not going to affect anyone because both those wages are still under the equilibrium wage of $7. So to answer the question, no workers will lose their jobs, and the unemployment rate is 0%. So I think I mentioned this last week maybe. The unemployment rate is 0% because the market is in equilibrium. The number of workers demanded equals the number of workers supplied. But that's more of a conceptual question. That was more of a conceptual question you had to figure out. But the last one goes back to some math. If instead the government voted to raise the minimum wage to $8 an hour, how many workers will lose their jobs, and what is the unemployment rate? So now this minimum wage of $8, it is binding because it's above the equilibrium wage. So even though $7 puts the market in equilibrium, from this price floor in the form of a minimum wage, they're not allowed to set that price of $7. They have to set it at $8 or higher. But most likely people will just keep it at $8. But anyway, we have to figure out how many workers lose their jobs and what the unemployment rate is. So for the first one, how many workers lose their jobs? So anyway, the new minimum wage is equal to $8. So how many workers will lose their jobs? So we have to look at the labor demand, because labor demand is how many workers firms want. So we have to look at the amount of workers wanted before the minimum wage law and after the minimum wage law and see if there's a difference in what firms are demanding. So looking back at our answer to part 1, before labor equaled 90. To figure out the amount wanted after, we just have to plug this new wage into our labor demand equation. So labor is going to equal 125 minus 5 times 8. So we can see this gives us a new labor level of 85. So what this is saying is if 90 workers were wanted before the wage change, but now only 85 workers are wanted, 5 workers are going to lose their jobs. And then they asked us to look at the unemployment rate. So we know the equation for the unemployment rate is equal to the number of unemployed over the amount in the labor force. They don't give us those concrete, they don't present the information in that definite way, like they've given us in previous problems. So we have to figure out how to solve each of these values using our idea of labor supply and demand. So I'm going to start with the labor force. So the labor force is like our labor supply because it's the total amount of people willing to work, the total amount of people in the labor force. So to find this labor force, we just have to plug in our wage at our minimum wage into the labor supply equation to see how many people are willing to work at a wage of $8. So we have labor supply equals 20 plus 10 times 8. And we can easily see that 20 plus 80 is 100. So we know that 100 people are in the labor force for this problem. Then we have to find the number of unemployed. So the number of unemployed is going to be the amount in the labor force minus the amount of people employed. But how many people are employed? The amount of people employed is going to be the amount that firms, the amount hired by firms, which is the amount demanded by firms, which we already solved for, which was 85. So we just solved for the labor force, which is 100. We can subtract the number of employed people, which is 85. The employed people are the people wanted by firms, like the amount of people demanded. So this difference comes to 15. And now, since we have the amount in the labor force, which is 100, the amount unemployed, which is 15, we can solve for our unemployment rate, which is going to be 15, the number of unemployed, over 100, the amount in the labor force. So our unemployment rate becomes 15%. And that is all we need to do for this problem. So that last one is a little bit harder to understand, just dealing with the minimum wage, whether it's binding or non-binding, and then using the idea of labor supply and demand to figure out the unemployment rate. But I think the easiest way to look at it is thinking of our labor force as labor supply and the amount of employed people as labor demand. And then using those two key concepts to figure out the rest of the equations needed to answer our question. But anyway, I understand this chapter, or these extra practice questions, were super long. Hopefully you were able to follow along, but the nice thing about these videos being posted is if you don't understand it, you can go back and replay it and watch it. I do have videos from other semesters up, so in case I might have said something in a better way, those times you could try looking back at those. But that is all for today, and best of luck in your studying.